Life is a simpler word to say, but it has puzzled philosophers, naturalists, and biologists for thousands of years. It is probably the most complex chemical and physical process in the universe. It's so astonishing that we might assume this jewel of biology is something unique to Earth, a rarity in the cosmos, something that only happened here and will never happen again. And yet, at the same time, we've tried to communicate with space, sending radio signals to the stars, hoping perhaps for some kind of answer from the darkness. Since the 1992, we've discovered more than 5,000 planets outside our solar system, and that completely changed how we look at the possibilities for life in the universe. We now know that Earth-like planets are far more common than we once believed. With the discovery of those thousands of exoplanets, the science of astrobiology, or exobiology, was truly born. For the first time, we could talk about life beyond Earth in a scientific way, and not just as a fantasy there. In just a few decades, extraterrestrial life stopped being only a theme for novels and films, and started to be treated as a real possibility, so real that we've invested billions of dollars in new telescopes to search for it. For this reason, today you're going to see why it's possible that we are the generation that will witness the most important discovery in history, proving that extraterrestrial life exists. Although, of course, it might be very different from how we imagine it. You will also discover when and how planet Earth will die. You will learn about regions of the universe where almost nothing can exist anymore. You'll better understand just how rare and special our planet is, with all its life and diversity. And with that, we'll try to answer a big question. Where is everyone else? And, in the end, you may never look at the sky in quite the same way again. These are some of the possible reasons for that great silence. One of the best-known ways to estimate how many active civilizations might exist in the Milky Way. Civilizations capable of communicating with us is the Drake equation, proposed in 1961. This equation combines several variables whose estimates can vary enormously. How many stars there are in the galaxy? How many of them have planets? How many of those planets resemble Earth? How many are in the habitable zone? How many develop life? How many generate complex and intelligent life? And, finally, how many become capable of communication? What's fascinating is that, depending on the values you choose for each term, the galaxy can end up looking practically empty or crammed full of civilizations. That huge uncertainty is part of the so-called Fermi paradox. If intelligent life isn't so rare, why don't we see clear signs of anyone else? Maybe most civilizations self-destruct before they can colonize the galaxy, or perhaps distances are so immense that they almost never overlap in time. It's also so possible that we're searching at the wrong frequencies, or that intelligent life prefers not to draw attention to itself. Each of these possibilities tells us something uncomfortable, but very profound, about our own future as a species. Understanding that silence may be just as important is, one day, finding the first signal that we are not alone. In our galaxy alone, there might be close to 500 billion stars. And in the entire universe, more than 2 trillion galaxies. That means there could be quadrillions, or even quintillions of possible places where life might appear, or perhaps many more. So, according to Drake himself, in our galaxy alone there could right now be anywhere between 1,000 and 100 million intelligent civilizations. For him, it was much harder to believe that we are alone than to believe the opposite. He died imagining a universe full of life. From there comes the famous Fermi paradox, which poses a very simple but unsettling question. If the universe is so big and the odds of life are so high, where is everybody? Why have projects dedicated to searching for extraterrestrial life, such as NASA's SETI program, never produced truly promising results, at least as far as we know? Will the golden records aboard the Voyager probes ever be intercepted and appreciated by some form of life similar enough to us to understand their meaning? If that happened, they would find a very valuable record of what humanity was: music, greetings in dozens of languages, and photographs of life on Earth. Those records contain enough information for others to be able to locate us, even if they arrive here long after our extinction, since the probes will survive for billions of years and travel across the entire galaxy. For now, we don't know of any other planets with life, but at least we have one great example: Earth. By studying the history of our own planet, we're beginning to build a foundation for imagining what life might be like elsewhere in the universe. Let's try to understand the life expectancy of Earth's biosphere, and at what point it reaches its maximum potential, from the planet's formation to its destruction. But to grasp this, we have to travel back in time around 4,700,000,000 years to the birth of our planet, the so-called chaotic eon. At that moment, the universe was about 9 billion years old, and many generations of giant stars had already been born and died. These very short-lived stars exploded spectacularly at the end of their existence. They were supernovae. In those explosions, the heavy elements of the periodic table were forged. They still occur today. They are the dramatic end of the largest stars in the universe. Thanks to those violent explosions, interstellar space gradually filled with carbon, oxygen, iron, silicon, and many other elements essential for forming rocky planets and later living beings. Every calcium atom in your bones, every iron atom in your blood, was once born inside a star that eventually exploded. Earth formed out of that recycled material in an incredibly hostile environment, bombarded by meteorites and subjected to extreme volcanic activity. However, that initial chaos was also an opportunity. It brought water, organic compounds, and enough energy for the first self-replicating molecules to appear at some point. Understanding this violent, cosmic origin of our planet reminds us that life did not emerge in spite of the universe, but thanks to its most brutal and magnificent processes. And if it happened here, in some random corner of the Milky Way, maybe it can happen again in many other places. The smallest stars, by contrast, shine less brightly, are cooler, and live far longer. Our sun is bigger than most stars in the universe, but it's far from being among the largest. It formed inside a nebula, an enormous cloud of gas where stars are born. Around that protostar, a protoplanetary disk appeared, a kind of ring of gas, dust, and rocks where, through collisions and gradual accumulation of matter, planets and other bodies formed. In one small region of that disk, Proto-Earth and Theia, two protoplanets in the final phase of their formation, were competing for the same orbit. Their gravitational dance ended in a gigantic impact that gave rise both to Earth and to the Moon. That collision didn't just create the Moon, it also stirred up Earth's interior, melted much of its surface, and may have helped it differentiate into core, mantle, and crust. On top of that, the presence of the Moon stabilized our planet's axis of rotation and generated strong tides, which would later play an important role in the chemistry of the first coasts and seas. That's when the Hadean Aeon began, the first hellish billions of years of our planet. It was in that hot, dark, electrically charged chemical soup that the first living beings emerged. We might think those conditions were too extreme for life, but the latest studies suggest the opposite. That extreme environment was precisely what made life possible. It's likely that the first organisms arose near hydrothermal vents on the ocean floor, where the planet's internal heat powered highly energetic chemical reactions. And that's good news, because it suggests that life might be relatively common when the right conditions are in place, rocky planets with liquid water on their surfaces. What if the very chemical oven of planet formation were enough to create life? That would mean many rocky planets could generate life very early in their history. But the appearance of life is only the first step. Its persistence is another matter. As we'll see, a lot of stable conditions are needed for a planet to remain habitable for billions of years. There's an endless list of disasters that can sterilize it: the death of a nearby star, the passage of a body that disturbs its orbit, a major collision, internal changes within the planet itself. Mars and Venus, for example, may have been just as habitable as Earth billions of years ago, but their evolution ultimately turned them into inhospitable worlds. Mars lost most of its atmosphere and water, ending up as a frozen desert. Venus, on the other hand, fell into a runaway greenhouse effect and became a toxic oven. Earth, between those two extremes, managed to stay within a very narrow band of balance. That band is what many other worlds may now be struggling to hold onto in some hidden corner of the galaxy. Venus, being too close to the Sun, suffered an out-of-control greenhouse effect. Its atmosphere is very dense and rich in carbon dioxide, trapping heat to an extreme degree. Temperatures on the surface exceed 460 grados Celsius, enough to melt lead. Mars, by contrast, was too small. Its core cooled quickly, it lost its magnetic field and, with it, its atmosphere. The solar wind gradually stripped it away, leaving behind a cold, dry world. Earth was luckier. It ended up in exactly the right spot. It has the right size, a stable atmosphere, and it lies at the right distance from the sun to maintain liquid water and a relatively stable climate for billions of years. In addition, its magnetic field acts as a shield against the solar wind, and plate tectonics helps recycle carbon dioxide, preventing the greenhouse effect from either spiraling out of control or disappearing entirely. It's a fragile balance, but it has worked for a very long time. In those first oceans, life probably began with molecules capable of copying themselves, as small fragments of self-replicating RNA. Over time, these simple systems became enclosed in membranes, forming protocells. The next big step was cooperation. Some of those chemical units began to join together, to specialize in different functions, and to exchange energy and matter. That's when biology truly began. Somehow, from that chaotic chemistry, a common ancestor of all living beings we know today emerged from bacteria to humans. The oldest fossils we know of are microbes found in rocks in Western Australia, about 3.5 billion years old. This means life arose very soon after the planet formed. Only a few 100 million years after the initial chaos, there were already bacteria capable of photosynthesis. They were so successful that they changed the entire planet. They released oxygen into the atmosphere and permanently altered the chemistry of the oceans. We call this event the Great Oxidation, and it occurred about 2.4 billion years ago. Oxygen was both a blessing and a curse. For most anaerobic microorganisms that lived without oxygen, it was a poison, and many of them disappeared. But others learned to use it as a source of energy, and that's how cellular respiration was born. This metabolic revolution allowed larger, more complex, and more active organisms to appear. For the next billion years, Earth was a planet dominated by microbes. But once again, cooperation changed everything. Some bacteria began living inside others in a relationship so close that they eventually fused. This is how eukaryotic cells arose, with a nucleus and internal organelles such as mitochondria. This was one of the most important steps in all of evolution. Without it, there would be no animals, plants, or fungi. From that moment on, life had giant cells, far more versatile, capable of forming tissues, organs, and, in time, entire ecosystems as complex as those we see today. The first multicellular organisms appeared about 600 million years ago in the oceans of the Ediacaran period. They had no skeletons or shells, but they did form bodies with different types of specialized tissues. They were strange creatures with leaf-like, disc-shaped, or ribbon-shaped bodies stuck to the seafloor as if they were living carpets. Later, in the Cambrian, about 541 million years ago, something extraordinary happened. The Cambrian explosion. In a very short geological time span, almost all the basic animal body plans we know today appeared. Arthropods, mollusks, chordates, echinoderms. It was an explosion of biological diversity without precedent. The sea is filled with bizarre creatures, and the struggle to survive made evolution speed up. Predators and prey appeared, along with shells, claws, teeth, and increasingly complex eyes. Food chains became more elaborate, and natural selection acted with great intensity. Some species disappeared quickly, others diversified into hundreds of different forms. From that point on, life began to experiment with every possible strategy: burrowing, swimming, filtering, hunting, and fleeing. Around 450 million years ago, plants began to conquer dry land. Then came insects and amphibians. The landscape turned green, and oxygen in the atmosphere rose even further. Later, reptiles appeared, and among them the dinosaurs, which dominated Earth for more than 160 million years. But even they were destined to vanish. During that long reign, there were several extinctions, climate changes, and complete reorganizations of ecosystems. 66 million years ago, an asteroid about 10 kilometers wide slammed into what is now Mexico's Yucatan Peninsula. The energy released was so enormous that it wiped out around 75% of the planet's species, including almost all the dinosaurs. Yet that catastrophe opened the way for mammals, small, nocturnal, and opportunistic. Mammals survive hidden in burrows and forests, waiting for their chance. Over time, some became larger, more intelligent, and more social. Among them, a group of primates began developing very skillful hands and increasingly complex brains. Their home was the tropical forests of Africa. There they learned to cooperate, to care for their young for longer periods, and to communicate in ever more sophisticated ways. For millions of years, those primates changed in order to adapt to a planet in constant transformation. The climate shifted, ice ages came, and savannas expanded. That forced them to stand up on two legs to see over the tall grass and free their hands. Walking upright was the first big step toward what we now call humanity. From then on, culture, technology, and language would begin to play a role just as important as biology itself. Australopithecus, one of our oldest ancestors, was already walking on two legs more than 3 million years ago. It had a small brain but great curiosity. It probably split its time between the trees and the ground, gathering fruits, scavenging animal remains, and exploring its surroundings. It made very simple stone tools and lived in groups. Its world was full of Danger's big cats, hyenas, crocodiles, but also full of opportunities to learn, share, and cooperate. From those Australopithecus, about those 0.5 million years ago, the genus Homo appeared. And with it, a new kind of intelligence. One that not only served to survive, but also to imagine and plan. Homo habilis, Homo erectus, Homo heidelbergensis, the Neanderthals, and finally us. Each species added something new. Better control of fire, greater ability to walk long distances, more complex tools, the seed of symbolic thought. By mastering fire, the first humans tamed one of the most powerful forces in nature. They learned to cook, to keep warm at night, to scare off predators, and to gather around the flames. Those first campfires were our first homes. Culture was born there. Around the fire, people told stories, shared knowledge, and strengthened group bonds. Perhaps that's also where the first myths appeared, the first shared fears, and the first explanations about the sky and death. Fire also changed our bodies. Cooked food is easier to digest and yields more energy. That extra energy allowed the brain to grow and become the most energy-hungry organ in the body. So fire didn't just transform what we ate. It also helped shape our intelligence and our social life, because it favored long gatherings, conversations, and cooperation. Homo erectus, for its part, was the first to leave Africa. Thanks to its ingenuity, it made increasingly precise tools, hand axes, bifaces, spears. It was also the first to walk fully upright, with a body quite similar to ours. It was a tireless traveler, able to adapt to very different climates. Later came species such as Homo heidelbergensis and eventually the Neanderthals, who lived in Europe for hundreds of thousands of years. Far from the stereotype of the clumsy, brutal caveman, Neanderthals were sophisticated. They made tools, buried their dead, cared for the sick and elderly, and mastered fire. They probably had some form of language and perhaps simple artistic expression. They were as human as we are, though with a different appearance and perhaps a different way of feeling. The Neanderthals were our cousins, not our enemies. In fact, we share some of our DNA with them, about 2% in most known African populations. This means that at some point we not only lived alongside them, but also interbred with them. It's possible that many traits we now consider human physical resilience, immune system defenses, even aspects of personality are the result of that ancient mixing. We are, in reality, the outcome of many human lineages crossing paths, a mixed species that carries within it the genetic memory of other humans who are no longer here. Meanwhile, in Africa, a new species was emerging, Homo sapiens, us. We had a more rounded brain case, a high forehead, and a capacity for symbolic thought never seen before. Our greatest weapon was not strength, but imagination. We learned to create worlds in our minds, to plan for the future, to dream, to believe. We began painting animals and spirits on cave walls, wearing necklaces, pigments, and ornaments that were useless for hunting or eating, but very useful for saying who we are within the group. About 70,000 years ago, our species began to spread out of Africa, carrying with it fire, language, and stories. We crossed deserts, jungles, glaciers, and seas. We arrived in Asia, Europe, Oceania, and finally the Americas. In each new place, humans transformed the landscape, domesticated animals, invented tools, and developed music, art, and spirituality. Wherever human footprints appeared, so did myths, rituals, and ways of explaining the world. Spoken language was another major turning point. It made it possible to share complex ideas, organize large groups, and create cultures. Words gave us power over time. Thanks to them, we could remember the past and imagine the future. Historical consciousness was born that way. Language also allowed us to coordinate collective work, building shelters, planning hunts, distributing tasks, making decisions as a group. A well-told story could unite hundreds or thousands of people who had never met. And that's how our ability to cooperate in large groups turned us into the dominant species on the planet. We are the only animals capable of collaborating on a massive scale with strangers based on shared ideas, religions, laws, money, flags. Thanks to that, we could build civilizations. First came agriculture and the first villages. Later, cities, empires, libraries, universities, and global networks. But that same capacity to create also gave us the power to destroy. The mind that painted the caves of Lascaux and raised the pyramids is the same mind that invented nuclear weapons and large-scale deforestation. This duality has been with us from the beginning. We are both creators and destroyers, dreamers and executioners. We can protect a sacred forest for generations, or cut it down in a few decades. In just a few thousand years, we went from making stone axes to launching rockets into space. If all of Earth's history were compressed into a single year, human history from the first cave paintings to today would fit into only the last few minutes of December 31. And even so, those few minutes have been enough to completely transform the planet. We have triggered a new geological era marked by our own footprint. We have diverted rivers, altered winds, and flattened mountains. Nature didn't disappear, but it became entangled with the human world. And, almost without noticing it, we began to see ourselves as something separate from the nature that created us. We forgot that we still depend on the air, the water, the soil, and on millions of invisible species. Only now are we starting to realize that, if we want a future, we'll have to reconcile with the planet we came from. Yet, everything we build comes from the Earth. The phone you're using to watch this video is made of metals, water, and sand. The same materials used to make the first stone tools. The electricity that powers it comes from chemical reactions, from the wind, from the sun, or from ancient forests turned into coal and oil. Human beings have never stopped shaping nature. We've simply learned to do it with far more precision on both microscopic and planetary scales at the same time. Our story is one of a highly unlikely ascent, from being defenseless prey on African savannas to becoming the dominant species on the planet. But that victory has a cost. Along the way, we've left extinctions, deserts, and deep scars behind us. Sometimes we see ourselves as gods, but we are still animals that need air, water, and a suitable temperature to survive. No technology has changed that basic fact. With the advent of agriculture about 10,000 years ago, we made a decisive turn. We learned to domesticate plants and animals and stopped depending completely on hunting and gathering. The first permanent settlements were born, then villages, and later, cities. In places like Mesopotamia, Egypt, the Indus Valley, or China, rivers became the center of life and civilization. Calendars were designed to know when to sow, myths to explain the floods, and the first engineering works to control them. Agriculture brought stability, but also inequality. Since people could store food surpluses, some groups began to control wealth and power. Kings, templars, and armies appeared, and with them, war. Civilizations rose and fell again and again, leaving their marks in stone, clay, and papyrus. Each one left a lesson: how to organize millions of people, and also how to collapse when resources are overexploited or power becomes too concentrated. About 10,000 years ago, we invented writing. Thanks to it, history stopped being transmitted only orally and began to be recorded. We could write down laws, lists, poems, agreements, and, above all, memories. The written word was like a new kind of fire, a way of lighting up thought through time. Allowed an idea to leap from one generation to another without being completely lost, and it allowed a person to speak to the future. Science, philosophy, and religion, each in their own way, have always tried to answer the same big questions. Where do we come from? Who are we? Where are we going? Even though our answers have grown more complex, the questions are the same ones our ancestors asked under the starry sky. Only the stage has changed. Before, they looked at campfires and temples. Now, we look at screens and telescopes. Even so, in recent centuries humanity has advanced at an unprecedented speed. In just a few hundred years we discovered electricity, the engine, antibiotics, the airplane, the computer, and DNA. Today we send probes to the edges of the solar system and observe galaxies billions of light years away. But at the same time, we've pushed the planet to the brink of collapse. The same ingenuity that has allowed us to understand the stars is altering the climate, melting ice, and driving species to extinction. Our great test as a civilization will be to find out whether that intelligence is capable of stopping its own impact in time. Our civilization is built on a paradox. We use the intelligence that evolution gave us to jeopardize the very conditions that made our existence possible. We have altered the climate, the oceans, and the atmosphere. We're driving species to extinction faster than new ones appear. And we're turning Earth's resources into waste faster than nature can absorb it. We are capable of measuring that damage precisely, drawing graphs, writing reports and forecasts. And yet, many times, we keep acting as if it had nothing to do with us. If we keep going this way, we could become the victims of our own success. The Anthropocene, the geological epoch marked by human activity, could also be the beginning of our downfall. But all is not lost. Just as we can devastate a forest in a few years, we can also replant it, protect it, and leave it in better shape for future generations. Our impact is enormous, but so is our capacity to change course. That same intelligence that allowed us to master fire and electricity can help us get out of this mess. No other species has had such a capacity to change its own destiny. Today we have the knowledge to reverse much of the damage. We can restore ecosystems, rebalance the climate, and learn to live in harmony with the planet that gave us life. We have renewable energies, conservation techniques, regenerative agriculture, and tools for global cooperation that have never existed before. The main challenge, however, is not technological but morale. We need to once again feel ourselves part of nature, not its owners. To remember that the air we breathe and the water we drink are part of the same cycle that sustains every tree, every fish, every cloud. We are not mere observers of the world. We are the world becoming aware of itself. Taking care of the planet is, deep down, a way of taking care of ourselves. Looking toward the future is like looking into a mirror. If we manage to overcome our own arrogance, we can become guardians of life instead of its executioners. We can use our creativity to protect rather than destroy. Perhaps that will be the next evolutionary step, not of the body, but of consciousness. An evolution not measured in bones or genes, but in empathy, responsibility, and the ability to imagine better futures. Because, in the end, evolution does not end with us. We are only one chapter in a much longer story, the story of the universe trying to understand itself. And if we learn to listen, the silence of the cosmos does not mean emptiness. It becomes an invitation to keep exploring, to keep creating, to keep caring. To remember that, even though we mastered fire, we are still stardust. That the iron in our blood and the calcium in our bones were formed in the hearts of ancient supernovae. And that someday, everything we are will return to the stars. In the meantime, we have a brief but immense task to ensure that this small corner of the universe remains habitable, beautiful, and full of life. The history of humanity is, at its core, the history of the universe becoming conscious of itself. Every atom in your body was once part of a star that died billions of years ago. Everything you see, touch, and feel, from the water flowing through your veins to the light reaching your eyes, belongs to the same cosmic fabric. There is no real separation between you and the universe. You are one of its most complex reflections. When you look in the mirror, You are actually seeing stardust arranged in such a sophisticated way that it can ask itself what it is. If we condensed the entire history of the universe into a single year, the Big Bang would occur on January 1, and human beings would appear in the last seconds of December 31. All of written history, empires, religions, wars, art, science would fit into the final breath before midnight. And even so, those seconds have been enough to completely transform a planet. Never before, in that whole cosmic year, had a species altered its environment so much in so little time. For almost all of our time on Earth, we were insignificant, just one more species within the vast flow of evolution. But something in us lit up. A spark of consciousness allowed us to ask questions about the origin of the stars, the meaning of life, and our own destiny. That ability to ask questions more than strength or technology is what truly makes us human. An animal can flee from fire. We, in addition, ask ourselves what it is, why it burns, and how to harness it. We are children of chance and necessity, as the philosopher Jacques Monod put it, but we are also children of wonder. Without wonder, there would be no science. Without curiosity, we would never have crossed oceans or built telescopes. Without imagination, we would still be in the dark. Curiosity was, is, and will be our inner fire. It's what drives us to open books, to look out the window, to raise our eyes to the night sky and feel that there is something left to understand. But every flame needs care. If we use it to light the way, it can guide us toward a wiser future. If we use it to dominate, it can destroy us. Our mission is not to conquer the universe, but to understand it. And understanding it doesn't mean controlling it, but recognizing that we are an inseparable part of it. Perhaps true progress doesn't lie in going farther, but in better understanding where we are and what responsibility is implied by being alive in a universe that, for a brief moment, has learned to look at itself through our eyes. Maybe, deep down, evolution has no clear purpose. Or maybe its purpose is precisely this: to create beings capable of seeing the beauty of the world, of being moved by a sunrise, of loving another person, of looking at the sky and feeling gratitude. Perhaps this is what the cosmos was seeking, a way to experience itself through consciousness. We don't know whether there is any intention behind all this, but we do know that, for a fleeting instant on the scale of the universe, there exists something capable of saying this is beautiful and this matters. Now that we've traveled this long road from the first molecules to the deepest thoughts, one question remains. What are we going to do with this miracle? Will we keep raising borders, or will we finally learn to see ourselves as a single humanity? The Earth does not belong to us. We belong to the Earth. Every line on a map, every flag, is a mental construct. The air, the oceans, and the mountains don't understand countries. From space, our planet is just a blue sphere without divisions, fragile and luminous. When the last human being disappears, the universe will go on, immense and indifferent. Galaxies will keep spinning. Stars will go on being born and dying as if nothing had happened. But as long as we exist, every act of kindness, every discovery, every word that connects one mind to another is a way of extending the universe's life. Because, as long as there is consciousness, the universe is not completely alone. In every gesture of care, in every shared idea, there is a small victory against the void. This is what human evolution has been and still is. A story of light born from darkness, of fragility turned into power, of fear transformed into understanding. We have stumbled many times. We have caused harm, but we have also learned, apologized, rebuilt. And if this story teaches us anything, it is that true greatness does not lie in dominating the planet, but in caring for it. Not in being the strongest, but in being able to protect the most vulnerable human and non-human alike. We are the only species capable of choosing its destiny. We can look to the past and learn, look to the future and change. From being defenseless prey, we have become potential guardians of life. Perhaps that is the ultimate goal of evolution. Not dominance, but awareness. Not conquest, but compassion. For the species to stop thinking only of itself and begin to think about all of life is, in itself, an evolutionary leap. Because the universe didn't just give us life, it also gave us the ability to love. And as long as love exists, the cosmos will remain alive within us. Every time we care for someone, defend a forest, comfort a friend, or gaze at the stars with tenderness, we are, in our own way, answering that great cosmic question. And perhaps that answer is not made of words, but of something much simpler and deeper: the desire for life, wherever it may be, to keep on flourishing.